What if everything we can see, every star, every galaxy, every single planet, is only a tiny fraction of what's really out there? What if there's a hidden universe with its own unique particles and its own strange forces existing all around us, completely invisible? For decades, this has been more theory than fact. A kind of ghost story told with complex equations and mind-bending models. But what if we could finally test it? Deep within the data from the world's largest science experiment, physicists at CERN have developed a brand new way to search for proof. They're not looking for the loud, dramatic discoveries we've come to expect. They're listening for something much subtler, something stranger. A faint whisper of energy that doesn't match anything we know. This could be our first real shot at making contact with a hidden world, and it might just solve the single biggest mystery in all of physics. Section 1. The problem: the universe's biggest ghost. To get why this is such a big deal, we have to talk about a cosmic ghost. A phantom that shapes our entire universe but has stayed completely invisible. That ghost is called dark matter. Galaxies are spinning so fast that the gravity from all their visible stars, gas, and dust shouldn't be nearly enough to hold them together. They should have ripped themselves apart ages ago. It's like a merry-go-round spinning so fast the horses should go flying, but they just don't. Something is adding extra gravity, an invisible seatbelt holding everything in place. That something appears to outweigh all the matter we can see by a factor of nearly 6 to 1. When you do the math, the universe we know, the stuff making up you, me, and every star in the sky, is only about 5% of everything in the cosmos. The other 95% is a mix of dark energy and this mysterious dark matter, which alone makes up a whopping 27% of the universe. For the better part of a century, we've only known it's there because of its gravitational pull. We have never, not once, directly detected a single particle of it. It doesn't absorb, reflect, or emit light, making it profoundly, utterly dark. Finding it has become one of the most critical quests in science, because finding dark matter isn't just about bagging a new particle. It's about figuring out what most of our own universe is actually made of. Section 2. The setup. The machine that sees the unseeable. So how do you even begin to find something that's defined by being invisible? Well, you build the most powerful machine in human history. Welcome to CERN, the European Organization for Nuclear Research. Straddling the border of France and Switzerland, CERN is home to the Large Hadron Collider, or LHC. It's a 27-kilometer ring of superconducting magnets, chilled to a temperature colder than deep space. Inside this ring, tiny bunches of protons are revved up to 99.9999991% of the speed of light and then smashed into each other with incredible force. Why do this? Think of it like this. If you want to know how a watch works, you could just stare at it. But you'll learn a lot more, a lot faster, if you smash two of them together and study the tiny gears and springs that fly out. The LHC does that, but for reality itself. By recreating the energy levels that existed just moments after the Big Bang, physicists can glimpse the fundamental gears of the universe, the elementary particles that are the building blocks of everything. This is exactly how they found the famous Higgs boson, the particle that gives other particles their mass. Section 3. The climax. A whisper in the noise. And that brings us to the search. This isn't about a dramatic explosion or a clear signal of some heavy new particle. It's about something far more elusive. For the first time, researchers at one of the LHC's main experiments, the compact muon solenoid, CMS, have tested a totally new way to hunt for new physics. They started searching for something called soft, unclustered energy patterns. Picture the debris from a normal collision as shrapnel. A few big, high-energy pieces flying out in obvious directions. That's what physicists usually look for. But these soft patterns are different. They're more like a fine, spherical mist. A cloud of many low-energy particles spreading out in all directions. It's a whisper instead of a shout. A pattern that old-school searches might have missed completely. Section 4. The reality check. Science in action. Now, before we pop the champagne for finding a parallel universe, it is absolutely critical to say this loud and clear. This first search did not find a hidden world. The scientists at CMS analyzed data collected between 2016 and 2018 and found no excess of these strange, misty events beyond what our current theories predict. This is what's called a null result. But in science, a null result is far from a failure. It's incredibly useful. By not finding the signal, scientists were able to rule out certain possibilities. They set the first ever limits on some of these hidden valley scenarios, effectively telling theorists which versions of the idea are less likely and where to aim their search next. This is how science really works. It's not one big eureka moment, but a slow, careful process of crossing off dead ends and narrowing down the map to the treasure. Section 5. The broader search. More than one way to find a ghost. The hunt for a hidden world isn't just riding on one horse. CERN is launching a multi-pronged attack on this mystery, and the next decade is going to be absolutely thrilling. While the giant CMS and Atlas experiments look for hints in the chaos of head-on collisions, a totally different kind of experiment has been approved. SHIP, the search for hidden particles. SHIP won't smash particles together. Instead, it will take a high-intensity proton beam from CERN's superproton synchrotron and slam it into a dense block of metal. This will create a ridiculously huge number of known particles, which will then be absorbed by a massive shield. Section 6. The implications. What if they're right? So let's just take a step back and think about the stakes. What if one of these experiments hits the jackpot? What if that faint mist in CMS becomes a clear, undeniable signal in run 3? Or what if SHIP starts seeing particles magically appear in its detector? The implications would be nothing short of reality-altering. It would be the first definitive, experimental proof that the universe is fundamentally grander and more complex than we ever dreamed. It would confirm that the particles and forces we've studied for 100 years are just one layer of a much larger cosmic structure. This shadow sector, or hidden valley, would instantly transform from a theorist's dream into a confirmed part of our universe. More practically, it would likely give us our first real, tangible clue to the identity of dark matter. Dark matter would no longer be just an invisible source of gravity, but a substance made of particles we could start to study. Particles from a sector with its own rules, its own forces, and maybe even its own dark light. Centuries ago, ancient cartographers would draw maps that, at their very edges, simply said, "Here be dragons." It was their way of saying they had reached the limit of the known world. Today, physicists are standing at a similar edge. Our standard model of particle physics is a beautiful, incredibly detailed map, but we know it's incomplete. It doesn't include the 95% of the cosmos that is dark matter and dark energy. The search for a hidden sector at CERN is our generation's voyage into that uncharted territory. We have spent a century charting our little corner of the universe, only to realize we might be able to see just 5% of it. The question that drives thousands of scientists at CERN every single day is as simple as it is awe-inspiring. What else is out there?